We're going to be continuing on now to talk about string algorithms. And in particular, we're going to be talking about some ways of doing dynamic programming on strings. And the first thing that we're going to look at is we're going to look at an algorithm that is called the longest common subsequence. And truthfully, this is not specific to strings. It's just coming up in strings because it's something that you can kind of use there, but it actually has applications in other domains also. So after this, we will also talk about the process of edit distance. Okay, so that's the other algorithm that we'll discuss after this, but I'm going to spend some time talking about longest common subsequence first. Now, the thing to remember about a string is basically just an array of values. And the only thing that makes strings a little bit unique is that the number of different values that you can have at any one point in time is kind of limited. But the algorithm longest common subsequence is a common DP algorithm. It's sort of one of these classical dynamic programming algorithms. It's not really specific to strings, other than it's got some nice relations to edit distance that we'll see in a little bit. So that's why I'm discussing it here. So this is kind of a general dynamic programming talk, but it has the context of strings. So the idea of the longest common subsequence is that you're going to have two different arrays or two different strings, and you want to find what is the biggest subsequence that you can pull out of each one that is common to both of them. So I'll give you I'll write a real simple example here just so you can see it. Let's say that there are 6 A's here and there are 6 A's here. 1, 2, 3, 4. We'll make this a little longer. 1, 2, 3, 4, 5, 6. Okay, so out of both of these, and let's say that this one is filled with B's and this one is filled with C's. Okay, so it should be obvious to you that in both cases, the longest common subsequence that we can get is 6 A's. Okay, because we could pull a string of 6 A's out from the first one and similarly out from the second one. So it's a common subsequence and it's the longest one that we can achieve. Okay, so you can think about this in terms of a more general algorithm that if these were just numbers, so you had an array of numbers on two different arrays of numbers and you wanted to get what's the sort of common subsequence of numbers that you have along the way, that's the longest subsequence problem. And there are some ways that you can use it along the way. So I'm going to describe this just in general dynamic programming terms first. And so we'll call this algorithm LCS for longest common subsequence. And we will set this up as a dynamic programming problem. So let's assume that we've got our two strings. Let's call the first string S, and it is going to have values from characters from 1 to N. And the other one we'll call T, and it will have from 1 to, I'll say, M. Okay, well, we are going to form DP of I, J, will be the longest common subsequence of S just going from 1 to I with T going from 1 to J. Okay, so we're just going to say what's the longest common subsequence that we can get from S 1 to I and T 1 to J. And so some of these, they're like the base cases here are going to be kind of obvious, and the case that we want is kind of obvious. So hopefully it's obvious that what we want is NM. Is what we want. Okay, and the base cases that we know are that DP of 0J or DP of I 0, both of those are equal to 0. In other words, if we don't have any of the elements from S or T, so if none of the elements are there, if it's an empty string, the longest common subsequence is obviously 0. Okay, so this is going to be our base. This is going to be the thing that we want. And then we need to set up our recursion, just like every good dynamic programming problem. And the way we will write the recursion is we will say dp of I, j is going to be one of two things. So if s of I is equal to t of j, then this value is going to be 1 plus dp of I minus 1, j minus 1. Now, what do we mean by that? What that means is if I've got some string and there's a letter here that matches at the end of s, and I've got some string here and the same letter matches at the end of t, then obviously I have a match and I'm left with the dynamic programming problem where s is 1 less and t is 1 less. Okay, so that should be kind of obvious, and we match the last one. So there's never a reason we would not want to pull off the match from the end if that's the only thing we have. So if they both end there, well, obviously we want to match the last element since it does match, and we're left with two things after that. So this is kind of the base case if the things match. And then otherwise, otherwise they don't match. So instead of A, this might be B. And so we don't know. There's a couple of options. So we want to take the maximum of either taking one element off of S or taking one element off of T. Okay. In other words, if we have something like A, B, C, D, E, and the other one is X, Y, Z, A, B, okay, our two options then would be we want to compare A, B, C, D with X, Y, Z, A, B, or so that would be this option here, the second one, or sorry, that would be the first one because we reduced S by length 1. The other option would be that we would compare A, B, C, D, E with X, Y, Z, A. Okay, and that would be this second option. Okay, so just kind of undo all of this since it's not really important, but you get the idea that this is our dynamic programming problem that we have here along the way. Okay, so let's go through. I'm going to just do an example so that you can see how this works. And it is kind of long, but I think it will illustrate what's there. If you really understand this and it's clear, feel free to skip over this next part until we get to the end. So I'm going to give two strings here. The first one will be the string A, F, G, B, C, N, S, A, or P, D. Okay, and that will be, notice this is string S, and string T will be the letters R, T, A, D, B, C, F, P, A, D, G. So if you were to count these up, you can kind of see that if we start numbering, there should be, I believe, 11 letters in each one. Okay, so what we are going to do is we're going to form a table, and it's going to be a kind of complicated table, rather large, but this will be a 12 by 12 table. Okay, and do the same thing here. Okay, so there's my table. And what I'm going to have is up here, I will have T, and over here will be S. And these will be the entries for each of them. So starting with 0, that's why it was 12 by 12, even though there's only 11 characters. Remember, we started from 0. Okay, and we can look at our two strings now. And first of all, we can fill in the base cases. Remember, the base is if either string is length 0, then obviously the longest common subsequence is 0. And we could fill this in, we could fill this table in sort of in any direction, kind of working that way, because anytime we look at an element, the options are either going to be that one or that one if it doesn't match, or if it does match, we're going to go to that element of the table. So it's either I minus 1, which will be the one up, or it's j minus 1, which will be the one to the left, or it's both I minus 1 and j minus 1, which will be up and to the left. So as long as we kind of fill in our table left to right, top to bottom, it's going to be fine. Okay, so let's fill this in, and we'll look at all of the different cases. So I'm going to fill it in by going row by row with S. So I'm going to start out looking at the first element of S, which is A, and basically then we will check each one, and we're going to see if it's equal to the element of T. So we first of all look at this element of T, which is R. So do A and R match? No, they don't. So because of that, I'm going to take, remember, this is the one I'm comparing. If they don't match, I'm going to look at those two. If they do match, I'm going to add 1 to whatever is on the diagonal up to the left. Okay, so it doesn't match, so I take the minimum of those, which is just 0. I again go to this T. T does not match A, so it is again 0. Now we get to a point where the third element of T, so notice we're in column 3 of T, and row 1 for S, where T3 is equal to S1. So those are equal, so we're going to take 1 and add it to whatever came from the upper left. Okay, so that's where that 1 comes from. It says that the A in T matches the A in S. Okay, and so the next one, we're going to look at D and A, and obviously D and A don't match. So what we're going to do is take the minimum or the maximum of the two, one to the left or the one above it. Notice that over here we have a 1, so we will just go ahead and fill in 1 there. And likewise, we're going to fill in 1 all the way through. When we get all the way over here to number 9, that's this element right there, we could actually, we do have a match, and so we're really going to be adding 1 to whatever was up and to the left, since those matched, but it comes out to the same value. It's not any more. Okay, so the point here is for S1, if the only thing in S was the letter A, then the longest common subsequence between A and T would be of length 1. That's what we just calculated there along the way. Okay, let's go ahead and now look at the second element of T. This is an F, and you'll notice that in T down here, F only comes up in space 7. So we're not going to have a match anywhere in space 7. So for all of these, until we get to number 7, we are only going to take the maximum of the thing that's off to the left or the thing above it. So 0, 0, here there's a 1 above it, so we get a 1, 1, 1, 1. Now we get to 7. And again, because T7 matches up with S2, we will take whatever is off here to the right, and we will put the number 2 in there. And then there's no more matches down here to F, so we're just going to continue with that value the rest of the way across. Okay, we now come to S3. This is a G. Notice that G actually does match the very final element of T. But until then, we're just going to take the maximum of the thing to the left and the thing above. So 0, 0, here we get a 1, 1, 1, 1, 2, 2, 2, 2. And then finally, T11 does match up with S3. So we will add 1 to the thing that is up and to the left. So we get a 3 there. Okay, going on to number 4, there's a B. You'll notice that that matches up with T sub 5. So we will just use the max here until we get to T5. And at that point, we will use the thing that is up and to the left. And again, we take the max of the thing to the left and the thing above. So we get these values. Okay, so for for 5, this is a C now. Notice that we run into a C in place 6 in T. So we are going to just use the max all the way until we get to number 6. When we get to number 6, we will again go up and to the left. So that will be a 3 there. And there's no more C's that match. Therefore, we'll just keep using the max. Notice the max here is now the thing to the left. We've encountered a 3. And so we were done with that. Okay, when we go to number 6, this is the letter N. Notice N does not appear anywhere in T. So we're just going to take the maximum of the thing above and the thing to the left. And that basically just means that we copy the previous line in this case. The next letter is S. Again, it does not appear there. So it's very easy to fill this in. Okay, our next letter is an A. So this is SA. Notice that we get a match at T3. So at T3, we will get a match here, which will be 1. And it's actually meaning that it's 1 greater than that. That's where we get the value from. We also get a match all the way out at position number 9. So position 9 of T matches up with position 8 of S. So all of these will just take the max of the thing above until we get out to T9. And so at T9, we do in fact have 1 more than we had there. So we can write a 4, and the max of 3 and 4 is 4. And again, it's a 4. Okay, now we go on to the letter R. R does match. So S9 does match with T1. So, excuse me. So we get a match here. And so this is going to be 1, 1. And again, the match just continues on. So that doesn't actually improve things overall for us. By the end, we come to this P. Value of P, it's going to match T8. So everything here is just copied from above until we get all the way out to 8, at which point we are going to get a 4 there. I realized I did not draw that one in blue. And finally, we come to our last letter, which is D. And notice that D matches T4, and it matches T10. So all the way out to T4, we just keep what we had here, but at T4, we're going to get 1 larger. That. And this happens again at T10. So each time we just get the max of what's to the left and what's above. But here at T10, since T10 matches S11, we are going to increase what's on the diagonal by 1. And so we end up with 5. And so you can see that the final answer that we get is 5. That means that there is a common subsequence of length 5 between these two things. And actually, if we want to read it off, it is possible to go back through this process and just sort of trace where these things come from. So for instance, here, we could go there, and we might go here and here and here. There's actually 2 ways we could go there. We could have also gone over here like that. Either way works out the same way. Okay, and so if you want to, you can actually see what are the points where there was a common letter. Well, it's basically those points where there was a blue mark. So there's that one, there's that one, there's that one, and then you actually get a choice down there of either this one or this one. There's 2 different routes that we could have gone. And if you look at what those are the values of S1, they happened at S4, at S5, at either 8 or 10, so one of those 2, and at 11. So if I look at this, it was it was this A here. It was 1, 4, 5, let's say 8 and 11. And the alternative was, it could have been 10 and 11. And those, if we look at the same values here on T, they were the values 3, 5, 6, either 8 or 9, and 10. So again, those were the values 3, 5, 6, and then it was either 8 or 9. So if it was 8, it was that one. If it was 9, it was that. If it was 8, it was that. And then there's the B. Okay, so in either case, you do get a subsequence of length 5. So that was actually quite a bit of work to illustrate that, but hopefully it makes the process very clear. You see how dynamic programming works to find what that longest common subsequence is. Okay, now the LCS, if we can do that, it has some implications for another thing called the longest increasing subsequence, and I'll create a separate video, sort of a bonus dynamic programming video about the longest increasing subsequence. And you'll see how these two things are related, but I'll skip that for the moment. Okay, so I mentioned before that this process, even though I did this here with strings, with letters and things like that, it doesn't have to be done just with letters. It could have been done with any arrays of numbers, and this process would have worked just fine. The next algorithm that I'm going to talk about is one that tends to work better, or at least the place where you usually see it is with strings. And that is the question of edit distance. Okay, and the edit distance basically says, given two strings, how hard is it to transform one string into the other one? Okay, and so basically the question is, how hard, according to some cost function, is it to transform string S into string T? Okay, that's the edit distance problem. Okay, so as an example of what this is, I'll just do an example to show you in a second, but here are the possible edits that we are allowed. So we can either insert a space, we can delete a character, or we can change one character to another. And we can actually determine what our cost function is. So we can, call this C sub I, the cost to insert, and this the cost to delete. And the cost to change one character into another one would be the cost ij, where I is the first character and j is the second character, and we could have a different cost for each one. And so a way of doing this might be, a reason that you might want to do edit distance is if you're trying to find a word that someone mistyped and sort of see, oh, wait, what might they have mistyped? Well, it's very common to type, to press the wrong button on the keyboard. So like the Q and the W are next to each other on the keyboard. And so you might have a word that is supposed to be a word like which, and someone accidentally types QHICH. Well, W and Q, those should be pretty close together. And you wouldn't, and so there's a good chance that this is the word that they meant. And so you should be able to find that it's a word that has a very short edit distance from QHICH. And so the idea there would be you could set a different cost for each letter combination based perhaps on how close they are on the keyboard or how easily they're mistyped or something like that. Okay, so those are the different costs. You could just have the same cost for each one, like everything costs 1 or whatever, but that's up to you. You can set that up for any edit distance. Okay, so let me give you a quick example of a problem and what it would look like to do at an edit distance. Okay, so as an example here, let's say that we had the text problem. Put a space in here. Okay, let's say that we had the text problem solving, and we wanted to transform that into the text programming. Okay, so that's what we were trying to get to. So we could take a series of edits to get there, and some of these should seem kind of obvious to you. So the first thing we might do is we might do a few deletions. So let's delete the space. And then let's delete the S. And then let's delete the O. And let's delete the L. And then we will do a character change to change the B to a G. So notice this is the change here. And notice that what we are doing here is we're going to delete that, and then that, and then that, and then that. We will change the next character to an R. Then we will change the next one. Finally, the last character that's different. Okay, so basically we're changing just one character at a time there. So in this case, we had 4 deletions, and we had 4 changes of characters: B to G, L to R, E to A, V to M. And so we could compute what the cost is. And there's other ways we could have done this. For instance, we didn't have to necessarily delete exactly those characters, and it might have been that some other combination would have worked well. Notice that we could have gone the other direction here to go from programming to problem solving. We could have changed some of these letters around, and then instead of deleting a character, we might insert a space and then change the space to the letter. So for instance, to go from this one to this one, we would insert a space and then we would change the space to an L. Okay, so there's different ways of looking at the problem, but that's the idea of edit distance. So if we want to work with the edit distance problem, we can actually formulate this again as a dynamic programming problem. So let's think of a general DP way that we can describe this. So we will set our, well, first of all, let's just say we have our 2 strings, just like before, S, which is going from 1 to N, and we have T, which is going from 1 to M, and we are going to set DP of ij, and this should look kind of similar to what we did for LCS. DP of ij is going to be the maximum score, so that we're wanting to get like the highest score possible, shows that the two things are as close together as we can get. Like a high score means the 2 strings are really similar, and a low score means they're not very similar. So we want to get the maximum score for S from 1 to I, and T from 1 to J. Okay, so that's going to be how we define DP, and we're going to have to actually decide on kind of what values we give to deletion and insertion and what it takes to match or change one thing to another. So this can get kind of complicated, but I'll do sort of the simple one, and you can look up ways of making this slightly more complicated if you want to. But basically, we've got dp of 0, 0. So if there's nothing there, then that is 0. There's obviously no score. And the other base cases are dp of 0 times I, or 0i, or, I'm sorry, that should be j, or dp of I, 0. This is going to be j times the cost to delete, which I think I called CD. And this will be I times CD. So the cost to delete everything from I, or the cost to delete everything from J, is there. So that's the only way to compare the two. So basically you say, okay, if I'm comparing two things that are 0, the cost is 0, what would it take for me to edit something where I had J elements of T and none of S? Well, it would be the cost to delete everything from T. The sort of alternative to this is you can think of it as the cost to increase everything from I, but we'll just think of it in terms of kind of cost of deleting. Generally, the cost of, kind of like we saw up here with programming and problem solving, you can either do deletion in one direction or insertion and change in the other, and they come out basically the same. So usually you can treat them as one, and an easy way to think of it is you're just going to be deleting from one or the other. To get these two things to see how closely they match. So we have those as our base cases, and then our more general case is dp of ij is going to be the maximum of 3 different options. And so one of those options is we can say, okay, I'm going to actually look at the character that's in position ij. So we'll be left with whatever's left over after that, I minus 1, j minus 1, plus the, I'll call it the cost for s sub I and t sub j. And a typical way that this cost might be set up is that this is going to be plus 2 if, sorry, let me rewrite this, is that the cost of A, B equals 2 if A is equal to B, or minus 1 if A does not equal B. Okay, so if they're not equal, it's negative. If they are equal, it's positive. So basically what this is saying is one option is we look at the last element, we look at element ij, so I from S and T from J, and if those two things are the same, then we have we get like 2 points, and if they're different, it's minus 1 point, and then whatever we're left with is just the remainder of what's there, dp of I minus 1, j minus 1. So the other option is we could delete a character from each one. So we would have dp of I minus 1, j, or we would have dp of I, j, j minus 1. And this is going to be, this is going to have the cost for deleting an element there. So basically, this is going to be our deletion cost for CD, our cost for deleting from each of those. So if we delete one from J or delete one from I, then we sort of align them. And generally, our CD, a way of thinking about that is CD is usually equal to minus 1, similar to the cost of not having a match. Okay, so basically, you wouldn't want to do this. It's better to just, take both of them off if you know it's not going to match along the way. Okay, and so you can basically build up your DP problem this way. I am not going to go through the whole process because I already did that with the longest common subsequence. But the basic idea there is going to work very similar to what we had before with LCS, where we're going to be comparing the last element of the substrings, and we'll see whether it matches. If it does, that's great, and we get 2 points, and we go kind of up and to the left, or it doesn't match, in which case we can take the negative penalty and go up and to the left, Or, and this is something that we especially will need to do if the two things are different sizes, we might want to delete one or the other. And sometimes if you delete a character, then the rest of the stuff is going to align along the way, and everything will be good for us. So we'll get that deletion cost there. And again, the way to think of the deletion cost is very similar. It's basically the same as inserting a space to make everything line up along the way. Okay, so that's the longest common subsequent, I'm sorry, that's the edit distance problem. Another name for this, by the way, is the Levenshtein distance. That's another name for it besides edit distance. It's sometimes called Levenshtein distance. And again, you can actually make this a little bit more complicated by setting up different cost functions, and it makes your choices a little bit trickier and more complicated, but it will work there. Now, one thing that's interesting is to see how this is related to LCS. Okay, so we can get the longest common subsequence from the edit distance. And we can just do that by setting the penalty for a mismatch equals infinity. So in other words, we never want to, or like negative infinity, sorry. So it's like a negative infinity is the cost. So basically, we never want to have two things mismatched, but instead we have a penalty for a deletion is going to be 0. So it's better to just delete something that doesn't cost us anything. And then the points for a match are going to equal 1. And this will come out the same way. And basically what this means is it doesn't cost us, or we get a point every time we have a matching element, and we can delete an element for no cost. And if you kind of think back to how we set up the LCS dynamic programming and how we did the edit distance dynamic programming, this might make, you might be able to think that this makes sense. So basically, we never want to have the mismatch problem that edit distance allows us to have. Basically, we're not going to ever use that option. And instead, we're only either going to match the last element or we're going to delete. And so deleting, that's where you are at a box and you go either up or to the left. That's either deleting from S or deleting from T. Or the other option is we match, and that's when we go up to the right and we have an addition of 1. And so that turns out to be the exact same approach as we used earlier for LCS. So the point is, edit distance is like a more generalized version of the longest common subsequence problem. Okay, so if LCS made sense to you, edit distance, notice it's the same complexity. It's still an order n by m. You're still filling out a table of the same size. Again, and I didn't explicitly write it up here, but we are going to want dp of nm. Okay, so we would fill out a table that goes from 0 to n and 0 to m. So the table is the exact same size as we had before. We're just going to visit each cell of that table once. We do have to check, maybe it might be a more complicated check as far as what our options are at each cell in the table, but it's basically just a generalized version of our LCS problem. Okay, so again, those are a couple of examples of doing dynamic programming operations on strings. They let us do things like compute edit distance, which again is useful for trying to determine whether one word is close or far from another word, based on kind of how much work it would take to transform one into the other.